All right, listeners, buckle up, because today we're taking a deep dive into some seriously mind-bending physics.
Yeah, get ready for a wild ride.
We're going to be talking about these two papers by a physicist named L.S. Larkey, and he's proposing this totally new theory about why some atoms are stable and others, just decide to decay.
Right.
He calls it Fibonacci SMF RVS.
Catchy, right.
But the basic idea is, what if the stability of atoms, like the reason some elements hang around and others don't, what if that all boils down to them being like in tune with the vibrations of empty space itself?
Yeah, it's a pretty out there concept.
It really is. So where do we even begin with this? I mean, we kind of have to like redefine what empty space even means first, don't we?
Absolutely. That's a great place to start. Larkey uses this term, you'll see it a lot in his papers, RVS resonant vacuum state.
Okay.
And it's basically saying, look, we've been thinking about the vacuum of space as like this empty void.
Right.
But what if it's not empty at all? What if it's this like dynamic field of energy constantly vibrating, fluctuating?
So like a cosmic ocean or something.
Yeah, exactly. Like a cosmic ocean. But instead of water, it's pure energy.
Grow.
Yeah.
Okay, I'm trying to picture this. So you've got this energy ocean, this RVS.
Right.
But then how do atoms actually interact with it? Like, how do they ride these waves, if you will?
That's where those SMFs come in.
SMFs.
Yeah, subtle magnetic fields. Basically, Larkey's saying these tiny magnetic forces, they're everywhere in the universe. They can actually interact with the RVS.
Okay.
And by interacting with it, they shake those energy waves and create these little pockets of stability within the chaos.
So it's like these SMFs are like sculpting the cosmic ocean, making little coves where atoms can chill out.
Uh-huh. Yeah, that's a great way to put it. And here's where it gets even more mind-blowing.
Lay it on me.
Larkey believes that these pockets of stability, these coves in the ocean, they're not randomly scattered.
Oh.
He thinks they're arranged in a specific mathematical pattern based on something called Fibonacci scaling.
Hold on, Fibonacci. Is that like Fibonacci, like the spiral shell thing?
Yeah. You got it. The Fibonacci sequence creates that beautiful spiral pattern we see in nature, right?
Yeah.
From seashells to galaxies.
Right.
Well, Fibonacci scaling is similar, but it applies to how these stability pockets, these wave nodes, as Larkey calls them.
Wave nodes.
Wave nodes, yeah. How they're arranged within the RVS.
So you're saying that atoms are stable when they're sitting in one of these mathematically defined sweet spots in this energy ocean?
Exactly. They're like perfectly tuned to the resonant frequency of that particular wave node. And that minimizes their own internal energy, which basically translates to stability.
Okay, so that's stable atoms. They've found their Zen spot in the cosmic ocean.
Right.
What about the unstable ones, though? The ones that decay radioactively. Where do they fit into all of this?
Think of it like this. Imagine those unstable isotopes as buoys that are slightly off-node.
Off-node.
Yeah. Like they're not quite in those calm, stable spots. They're kind of caught in the choppy waters between those spots in the RVS.
So they're getting jostled around constantly by this energy, and that's what makes them unstable.
Precisely. They're in a higher energy state. They're uncomfortable. And they're looking for a way to move towards a more stable configuration.
And that's when they emit radiation, right? Like they're trying to shed energy to find a calmer spot in the ocean.
That's a great way to think about it.
Right.
And the type of radiation they emit, whether it's alpha particles, beta particles, gamma rays,
right,
it all depends on the specific way they're trying to reconfigure themselves to reach that stable wave node.
Okay, this is already getting pretty wild, but I'm curious, how does this all connect to those magic numbers we always hear about in nuclear physics? You know, those specific numbers of protons and neutrons that seem to make an isotope extra stable?
Ah, the magic numbers.
Right.
Yeah, that's one of the really fascinating things about Larkey's theory. He suggests that those magic numbers, which traditional nuclear physics tries to explain with the nuclear shell model,
Right.
he's saying they're actually indicators of particularly strong resonant wave nodes in the RVS.
So elements with magic numbers, they're basically sitting in the VIP section of the cosmic ocean, those super stable wave nodes.
You got it. They're like those buoys anchored in the calmest, most protected parts of the harbor.
And that's why they're so incredibly resistant to decay.
Exactly.
I gotta say, my mind is already kind of blown and we're just getting started.
Just wait till we get to Larkey's second paper. That's where things get really interesting.
Oh boy.
He takes this whole wave node theory to a whole new level. He actually proposes that if we could understand and control these subtle magnetic fields, those SMFs,
Yeah.
we might actually be able to manipulate radioactive decay.
Wait, are you serious? Like controlling the fate of atoms? That sounds like science fiction.
It does, doesn't it? But Larkey lays out some pretty specific ideas about how it might be possible.
I can't wait to hear about this.
And that's exactly what we'll be unpacking in the next part of our deep dive. Welcome back. So before we jump into the really out there stuff from Larkey's second paper,
Okay.
I think it's important to understand how he connects his wave node theory to those existing models of the nucleus.
Yeah, good point. We've been talking about this cosmic energy ocean and atoms being, in tune with it.
Right.
But how does that actually relate to the way scientists currently explain why some atoms are stable and others aren't?
So the mainstream model, the one you'll find in most textbooks, is called the nuclear shell model.
Okay, I've heard of that.
It basically explains stability based on how protons and neutrons are arranged within the nucleus.
Uh-huh.
Kind of like how electrons occupy shells around an atom.
Right.
And certain configurations, they're just more stable than others. And those correspond to what we call the magic numbers.
Okay, so are these two models, like the shell model and Larkey's wave node theory, are they totally incompatible?
Not necessarily. Larkey actually suggests that his model could explain the underlying reason why those shell configurations lead to stability in the first place.
Oh, interesting.
He's saying that those stable shell arrangements, they're the ones that best align with those stable wave nodes in the RVS.
So it's like the shell model is describing the internal structure of the atom, while Larkey's theory is explaining how that structure interacts with the external environment, this cosmic energy field.
Exactly. It's like zooming in and zooming out.
Mm-hmm.
You've got the shell model focused on the individual particles within the nucleus.
Uh-huh.
And then you zoom out and you see how the entire nucleus is interacting with this larger cosmic framework.
Okay, yeah, I'm starting to see how these ideas could maybe fit together. But let's get back to Larkey's second paper and those crazy implications.
Yeah.
He's actually suggesting that we could control radioactive decay. Like we could choose whether an atom decays or not.
Well, not exactly. It's more about influencing the process.
Yeah,
He proposes that if we could manipulate those SMFs,
the subtle magnetic fields.
right, if we could manipulate those, we could potentially influence the stability of isotopes.
So how would we even do that?
Okay, so get this. Larkey uses this really interesting analogy. He compares SMFs to tuning forks.
Tuning forks.
Yeah. You know how when you strike a tuning fork, it vibrates at a specific frequency?
Right, creates that resonant sound wave.
Exactly. Well, he suggests that we could use SMFs in a similar way.
So by generating very specific magnetic fields, we could create a resonance with the RVS.
You got it.
Yes.
It's like we could tune the vacuum to influence the stability of a particular isotope.
Whoa, that's pretty mind-blowing. So what would that look like in practice? Like, how would we actually use this technology?
Well, one of the most obvious applications would be in dealing with nuclear waste.
Oh, yeah, that's a huge problem.
Imagine being able to take highly radioactive waste, which right now we have to store for centuries,
Right.
and actually accelerate its decay into stable, harmless elements.
So no more need for those giant underground storage facilities.
Exactly. And it goes beyond just nuclear waste. Think about medicine.
Okay.
Radioactive isotopes are used in all sorts of diagnostic and therapeutic procedures.
Right.
But obviously their radioactivity poses risks. So if we could control their decay rate, make them decay faster.
We could make those procedures much safer. This all sounds incredible, but I have to ask, what about the risks? I mean, we'd be messing with some pretty fundamental forces here.
You're absolutely right.
Yeah.
The potential for unintended consequences is huge. We need to understand how these SMFs interact with the RVS inside and out.
Yeah.
Before we even thought about applying this technology.
We wouldn't want to accidentally create some new, even more dangerous form of radiation.
Exactly.
Yeah.
So yeah, a lot more research is needed before we start building atomic tuning forks or whatever.
I was going to say, but it's a pretty cool idea.
Oh, absolutely. And while Larkey's model, it's mathematically elegant and internally consistent.
Okay.
It's important to remember that it is still very speculative.
Yeah.
It hasn't been experimentally verified.
Right.
And it does challenge some pretty fundamental assumptions in physics.
But that's what makes it so exciting, right? It's pushing the boundaries of what we think is possible.
Exactly. It forces us to rethink our understanding of the universe.
Now, I know Larkey's papers get pretty deep into the math behind all of this.
Yeah, they do.
Can you give our listeners a taste of what that looks like without turning this into a physics lecture?
Sure. One of the key concepts he uses is something called Fibonacci recursion.
Fibonacci recursion.
It's similar to the Fibonacci sequence that we talked about earlier.
Right, the spiral thing.
Exactly. Larkey proposes that this mathematical pattern actually shows up in the arrangement of those stable wave nodes in the RVS.
So it's like a cosmic code that dictates where those pockets of stability can form.
Exactly. And those magic numbers, those special numbers of protons and neutrons, Larkey believes they actually correspond to particularly strong points in this Fibonacci sequence.
It's like those magic numbers are tuned in to the fundamental harmony of the universe.
That's a beautiful way to put it.
Yeah.
And this mathematical framework, it's how Larkey connects his theory to actual observable phenomena.
You're right.
He's not just throwing out random ideas, he's grounding them in mathematical principles.
Okay, that makes sense. So we've got this cosmic energy ocean, these subtle magnetic fields sculpting the waves, and this mathematical pattern dictating where the stable zones are. How does that all translate into radioactive decay?
So remember those unstable isotopes, the ones that are off-node?
Yeah.
Larkey's model suggests that they're constantly interacting with the RVS, trying to find a more stable wave configuration.
Okay.
And that process of trying to retune themselves, that's what leads to the emission of radiation.
So the type of radiation an unstable isotope emits, whether it's alpha, beta, or gamma, it depends on how it's trying to realign itself with those stable wave nodes.
Exactly. And the rate of decay, the half-life, it's basically a measure of how out of tune that isotope is with the RVS.
Interesting.
The further it is from a stable node, the more energetically uncomfortable it is, and the faster it decays.
It's kind of a beautiful model when you think about it.
It is. It really is.
He's created this grand, unified theory of nuclear stability connecting the subatomic world to the structure of the cosmos.
It's a great way to put it. It's a very ambitious and thought-provoking theory. And whether or not it ultimately proves to be correct, it really highlights the interconnectedness of everything in the universe.
Yeah, from the tiniest particles to the vast expanse of space.
Exactly.
Wow, we've covered some serious ground here. This whole concept of tuning atoms with magnetic fields, it's incredible.
It is.
I'm already wondering what kind of technology we might be able to develop if this all turns out to be true.
Well, that's what we'll explore in the final part of our deep dive.
Okay.
Along with some of the practical challenges and the ethical considerations that would come with such revolutionary technology.
Welcome back to our deep dive into Fibonacci, SMF, RVS, and all its craziness.
Well, it's been a wild ride.
So we've explored this theory about how atoms are like these tiny surfers riding the waves of the cosmic energy ocean.
Yeah.
We've talked about how subtle magnetic fields might be able to shake those waves. And now I want to talk about the future. What could this mean for technology? What kind of amazing things could we create if we could actually harness this power?
Well, I think it's important to remember that we're still in the realm of theory here.
Right, of course. But let's speculate a little bit. What if way down the line, this leads to some kind of technology that could actually transform elements?
Like turn lead into gold.
Yeah, or even something more practical. Imagine if we could neutralize nuclear waste.
That would be incredible. So in his second paper, Larkey outlines a potential technology that he calls oscillatory SMF chambers.
Oscillatory SMF chambers, what are those?
Basically, imagine a contained environment, maybe within a reactor or a waste processing facility,
Okay.
where we could generate these highly specific magnetic fields.
Yeah, and those fields would be oscillating,
Sounds like-
fluctuating at frequencies that match those stable wave nodes in the RVS.
Exactly.
Yeah.
And by carefully tuning those oscillations, we could nudge unstable isotopes towards those stable configurations.
So instead of blasting atoms apart with brute force, we'd be subtly guiding them towards a more harmonious state.
Yeah, it's like a much more elegant approach. But of course, the engineering challenges are immense.
Yeah, I can imagine. We're talking about controlling magnetic fields at the subatomic level.
Right, and creating a near-perfect vacuum to minimize interference, developing materials that can withstand those intense fields.
This sounds like technology that's centuries away, if it's even possible at all.
It probably is. But that's part of what I find so exciting about Larkey's work. It pushes us to think beyond the limitations of our current technology.
It's like a glimpse into a future where we might have this incredible level of control over matter.
And that control wouldn't come from brute force. It would come from a deep understanding of the universe's underlying harmony.
It's like we'd be learning to speak the language of the cosmos.
Exactly. And that language, it's written in mathematics and physics.
So for listeners who've been with us on this deep dive into Fibonacci, SMF, RVS, what's the one thing you really want them to take away from all of this?
I think the most important thing is to remember that science is about asking questions and challenging assumptions.
Right.
Larkey's model, it may or may not turn out to be correct, but it forces us to re-examine our understanding of nuclear physics and consider new possibilities.
It's a good reminder that we don't have all the answers yet.
Exactly. And maybe someday, far in the future, we'll look back at Larkey's work as the spark that ignited a whole new era of nuclear science.
An era where we can actually harness the power of those cosmic waves to reshape the world around us.
It's a pretty mind-blowing thought.
It really is. Well, thanks for joining us on this incredible journey through the world of Fibonacci SMF-RVS. Until next time, keep those minds curious.